In this video, I discuss why we have two equations to describe frictional forces and where the inequality comes from in the case of static friction. Let's take the simple example of someone pushing a fridge. Of course, to use Newton's laws, we're going to need to determine what are the net forces on our system, because the net forces on our system are equal to the mass of our system times the acceleration of our system. In order to do this, we're going to have to define our system. So I've drawn a dotted line around my fridge, that's my system, and now I can define what forces are acting on my system. I simply look at what is touching my system. There are two things in contact with my fridge: the hands of the person and the floor. Since those are the only things in contact with my system, they are the only things that can exert forces on my system other than gravity. And so if I looked at the hands will have each apply a force, but I'm just going to sum them together and call it totally a pushing force. And the floor can exert a force perpendicular to the floor. We call that the normal force. Normal, again, means perpendicular. And it can also apply a parallel force, which in this case will be friction. Friction is, of course, a force that prevents the floor from moving relative to the fridge, or the fridge moving relative to the floor. Of course, there's always gravity. Gravity is our one long-range force. And now we've got all our forces. We can draw our free body diagram. Our free body diagram, of course, has our normal force pointing upwards, the force of gravity pointing downwards, our pushing force pointing to the right, and our frictional force pointing to the left. Now, before we can apply Newton's second law is a vector equation. That's not very useful. So we're going to need to choose a coordinate axis. I'm going to choose good old up, down, left, right, where up is my positive direction and to the right is my positive direction. And now I can, from this, write my expression of Newton's second law. In the vertical direction, the y direction, I'm going to have the normal force minus my force of gravity, mg, is equal to the mass of my system times my acceleration in the y direction. In the horizontal direction, the x direction, I'm going to have two forces again. I'll have my pushing force, which is in the positive direction, so F push, minus my frictional force is equal to the mass of my system times my acceleration in the x direction. And now I can think about things. When I push on a fridge, I usually don't observe it flying up into the air, so I know my acceleration in the vertical direction, the y direction, should be 0. And that means that all of my acceleration must be in the x direction. So we have these expressions of Newton's second law for our system that tell us about the forces and the accelerations on our system. I'm going to stick with I'm going to ignore the vertical one and just stick with the horizontal one and look at what happens when I change my pushing force. So here you can see our expression of Newton's second law for my horizontal direction. And I've got a graph of the force of friction versus the pushing force. So as I increase my pushing force, what's going to happen to my force of friction? You'll notice when I'm not pushing, well, actually, you'll notice that when my fridge is not accelerating, my acceleration must be 0, and so these two forces must be equal. Now that means that when I'm not pushing at all, my frictional force must be 0. If I start pushing a little bit, well, my frictional force will go up immediately the same amount. So it's a linear relationship. And as I push harder and harder, my frictional force will increase to compensate. Notice the frictional force and the pushing force are always equal, but my acceleration continues to be 0. I haven't overcome friction enough to start this fridge moving, to start it accelerating. Now, I can push harder. Eventually, I'm going to reach a point where I hit some maximal friction force that's defined by my coefficient of static friction times my normal force. This is an empirical model. So this is my maximal force of friction. So all along this line, my pushing force and my frictional force must be equal, my frictional force is always less than this value of mu sub s, the coefficient of static friction, times the normal force. It's only when we reach right at the top that suddenly my frictional force equals this maximal value of the coefficient of static friction times the normal force. Now, if I push a little bit harder than that maximal force, suddenly I will begin to accelerate. Now my pushing force is greater than the maximum static friction, and so I'll begin to accelerate. And my equation has changed, you'll notice. Now it stays my pushing force minus my friction force, but I have some non-zero acceleration. What's even more interesting is because we're no longer in a static regime, we're in a kinetic regime, and now my frictional force will change. My frictional force will become instead the coefficient of kinetic friction times my normal force. And for most materials, the kinetic coefficient of friction is less than the static coefficient of friction. So as soon as I begin to move, my friction will decrease rapidly. And now my frictional force will be much, much larger. Even though I just pushed a little bit harder, my pushing force will be much, much larger than my frictional force because my frictional force has decreased so quickly. And I can continue pushing, and I'll continue to accelerate, but my frictional force never increases. My frictional force will continue to stay this constant value of the coefficient of kinetic friction times the normal force. So for everywhere beyond pushing at that coefficient of static friction times the normal force, that maximal value of the static friction, anytime I push harder than that, I will end up accelerating. And I'll end up accelerating in the direction of motion in this case. Now, what happens if we change this up a little? What happens if we come at it from the other direction? Now let's look at what happens when we come at friction from the kinetic regime. So we start with our fridge moving. We're going to start with a very large pushing force, so we have a very large acceleration because we still have this equation where we have the pushing force minus the friction force equals the mass of my system times the acceleration of my system. So I still have a very large acceleration because my pushing force is very large. As I decrease my pushing force, I will decrease along this straight line because my pushing force is going down, but my frictional force remains equal to the kinetic coefficient of friction times the normal force. So I'm going to come straight down along this line with my pushing force. Now notice my acceleration vector keeps getting smaller and smaller, but I'm still accelerating because my pushing force is still greater than that value of the frictional force. Eventually I'm going to reach the point where before we switched between static and kinetic regimes, right here where my pushing force is equal to the static coefficient of friction times the normal force. You'll notice because I was already moving, I'm in a kinetic regime. So I'm still pushing too hard. And that is because for most materials, my kinetic coefficient of friction is going to be less than my static coefficient of friction. And so my static coefficient times my normal force is still going to be larger than my kinetic coefficient times my normal force. So even though here was the point where we would transition to the static regime, you might think that, I'm in a kinetic regime and I'm still pushing too hard. So I'm not going to stop here. I can continue to decrease my pushing force and I will still be accelerating. Eventually though, I will hit the point where now my pushing force is equal to my kinetic coefficient of friction times my normal force. And now you'll notice my net force has gone to 0. So my net force is now 0. The difference between my two forces is 0 and my acceleration will be 0. That doesn't mean, however, that my fridge stops moving. No, remember there are two parts to Newton's first law. First part says if I'm at rest, I stay at rest when there are no net forces. The second part, though, says if I'm moving, I continue to move with constant velocity. when there are no net forces on my system. And so this fridge was moving. I've just barely balanced out the forces, so it will continue to move with constant velocity. It'll continue to move in this forward direction, the direction of motion, at a constant rate. And so everywhere in this regime, I will be speeding up. I'll be accelerating. My acceleration will have been in the direction of the motion of my fridge. And if I ease up a little bit more, well, now I'm no longer zero acceleration. Now I'm accelerating in a direction opposite the direction of motion. And so I'll have a small acceleration that is now slowing me down. But I will still be moving. I will still have this motion forward. The fridge didn't suddenly stop when my force went to zero. And so it's going to take some time to slow it down enough, especially if it had a very large velocity. A fridge generally has a very large mass, and so it has a very large inertia. Large inertia means it resists changing its velocity quite a lot, and so it takes a large acceleration to change its velocity very quickly. And I could go so far as to stop pushing it all. If I stop pushing it all, now my pushing force has gone to zero. And it's no longer present in my Newton's second law, my expression of Newton's second law. All that's there is now my frictional force. So my frictional force will exert a very large acceleration, or a much larger acceleration, but it is still kinetic, and so it is still equal to the kinetic coefficient of friction times the normal force. Of course, it is in the direction opposite the direction of motion. It is larger than it was before when I was pushing on it. And so my fridge is going to continue to slow down, but it may still have velocity. It may still be moving in the forward direction. And I could go so far as to pull on my fridge. Now, a pull is a negative pushing force, and so my pulling force and my frictional force are working together. They're pointing in the same direction. My frictional force is pointing against the direction of motion. My pulling force is pointing against the direction of motion. So I get a larger acceleration in the direction opposite the direction of motion. But my fridge has a large mass. And if it had a large velocity, even this modest acceleration may take some time to bring it fully to a stop. And so it may still be moving forwards. Really, it's running away from me. I'm trying to slow it down. And I'm working with friction to do so, but it's pulling me along. So we have these two ways that friction behaves, depending on whether we're going from a static regime to a kinetic regime, or from a kinetic regime to a static regime. If we start off in the static regime, so we start off not moving, and we increase our pushing force, we're going to increase up this line until we reach this maximal value for our friction force. And this is where then all along this line, our friction force and our pushing force are equal. It's only when we reach this point that we equal the maximum value. And so we have that our static friction is less than, and sometimes equal to, this maximal value of our friction force, where that maximal value is the static coefficient of friction times the normal force. If we push any harder, we will, of course, move straight forward along this line as we increase our pushing force. And that is because once we've jumped into the kinetic regime, and now our kinetic friction stays at a constant value, that value being the kinetic coefficient of friction times the normal force. On the other hand, if we started in a kinetic regime, then as we decrease our pushing force, we're going to come straight back along this line, and we will continue straight back along this line. Even as we hit the point where we transitioned before, we won't transition because we're still kinetic, we're still moving. When we reach the point where now our pushing force equals our kinetic friction, this is the point where we'll get a net force equal to 0. And again, this is assuming that we only have those two forces in our horizontal direction. So we'll get a net force equal to 0. And this is where our velocity becomes constant. But our velocity does not become 0. So we still are moving. Everywhere above this line, we are speeding up. Once we get below that line, we will be slowing down because we'll have an acceleration pointing opposite the direction of motion. But what happens as we decrease below that line, we don't know. It all depends on what our velocity is. We could decrease and continue to decrease because we still haven't reached 0. We could decrease and then suddenly hit 0 velocity and go down along the line of our pushing force and our static friction force being equal. It all really depends on what our velocity is, because until we stop moving, we won't transition back into a static regime. So friction is quite odd because of this. This is, by the way, the property of hysteresis. It is the idea that the state of our system doesn't just depend on the values of our system, but it actually depends on how it reached those values. So it doesn't matter where you are so much as it doesn't only matter where you are, but it matters how you got there. Hysteresis is an effect that shows up in a lot of different systems. If you've ever dealt with chemistry, in chemistry, you might have seen supersaturated solutions, or supercooled or superheated systems. These are examples of hysteresis, where the state, again, depended on how you reached it. In common terms, you've probably even enjoyed some hysteresis because you've probably eaten candy, and the different candies that you get depend strongly on hysteresis to determine whether you're getting a hard candy that is a very large crystal formation, or whether you're getting something like a candy powder where you have very small crystals, that whether you're getting a nice smooth fudge. Fudge depends on hysteresis. So candy processes and candy making are replete with hysteresis. In materials, you'll find it show up in elasticity, because elastic properties often violate Hooke's law. We'll learn about Hooke's law later in the course. Hooke's law is often violated, and violations of Hooke's law are often because of hysteresis. And you'll also see it come up in magnetism. This is in physics 2. You'll see it in magnetism because permanent magnets depend on hysteresis to achieve their magnetism, their permanent magnetic states. So hysteresis is all over. I wanted you to understand how it shows up in friction, and how this is one of the things that causes friction to be a little bit odd. We have to treat it with some care, because we have to know not just what the state of the system is, but sort of how it got there, whether it was moving or not moving, what its velocity was before we can really analyze it. So take some care with friction. Understand that it does depend on how you reach that state.